Section 2 from Chapter 3 talks about addition and subtraction of whole numbers. Basically, we're going to look at a few ways to model addition and subtraction for whole numbers. No decimals, no fractions, just whole positive numbers. One of the first ideas talked about in the book is idea of counting on. So if we wanted to talk about counting on as a model for addition, let's think about a simple addition problem like 5 plus 3. Counting on tells you to start at 5 because that's the first number of the two that you're adding. So start at 5 on the number line and then move up along the number line 3 times. 1, 2, 3. And then look at where you've landed. We landed on 8, which means 5 plus 3 must be 8. So this is a way of modeling addition using counting on. Now, of course, most of us know how to add already. But remember, you're in a class of people who want to become teachers. So if you're showing this to a student who's never heard of addition before, this can be a valuable tool to help put a picture to the words that you're telling them. Another model is the set model, and this is where you use blocks or some kind of physical manipulative to hold in your hands that you can move around, slide around on the table. Now in Chapter 2, we talked about sets, and you wouldn't present sets to a child learning addition, but instead you would understand how to explain addition using sets. So we could have a set A with 4 blocks in it, a set B with 3 blocks in it, and if we're adding them together, we're unioning those two sets, we're combining them all into one circle. That's 4 plus 3. We count in the combined circle that there are 7 units. Now we've talked about sets that can overlap. If we're trying to use union to represent addition, we have to make sure that our sets are disjoint. Remember, disjoint means they have no elements in common. And we can see that the sets A and B in our diagram do not have any common elements. They both have completely different lettered boxes. We can also use a number line model if we're looking at a word problem like Josh has 4 feet of red ribbon and 3 feet of white ribbon. How many feet of ribbon in total, both counting the red and the white ribbon, does he have together? Well, we can draw a number line and lay the ribbon on the number line to show there's 2 separate pieces of ribbon. So we have the red ribbon here represented by the 4, and we have the white ribbon represented by the 3, and then we can see where it starts, and we can see where the 2 ribbons stop, and we can see from 0 to the end we are at 7. So addition using a number line can also be helpful. One of the addition properties that's really important to communicate is that addition is commutative, meaning you can reverse the order of the numbers and it won't change the value. 3 plus 5 is the same as 5 plus 3. And we can use a number line, for example, to illustrate this idea. Notice that in the top half of this diagram, the 3 shows up first, and then the 5. But in the bottom half of the diagram, the 3 shows up second, after the 5. But both of the additions start at 0 and stop at 8. So this is a way to demonstrate it's not important which number comes first when we're talking about addition. There's definitely a place for memorization, and it's important to memorize certain facts, but you might need to have a little bridge that gets you from I just learned addition to now I have all the facts memorized. If you skip that bridge about how addition works and you just go to memorize, we're going to have a bunch of mathematically illiterate people running our country in the future. So instead of telling them, don't worry about how addition works, just worry about what the answer is, we want to make sure that they can quickly get to the answer using mathematical logic. So counting on is a quick way to add two things. If you've ever noticed when students are learning addition and they try to use their fingers, if they do 4 plus 2, if they start counting 1, 2, 3, 4, they're wasting a little bit of time. They should start at 4 and then count 5, 6 to add the 2. Another thing that we can do to help quickly get to addition answers is using doubles. Now, if you think about 3 plus 3 or 4 plus 4, those are small facts that we can memorize and then use those few memorization tools to help find other answers quickly. For example, if we're looking at 6 plus 7, we can say, oh man, that's a lot like 6 plus 6, which I memorized is 12. The only difference is that instead of adding 6 and 6, I'm adding 6 and 7. Well, 7 is one more. So I can just say, instead of 6 plus 7, let's do 6 plus 6 plus 1. Since I know 6 plus 6 is 12, I'm really just doing 12 plus 1. So doubles is another way to quickly come to addition answers. Making 10 is one of my favorite shortcuts. When you're adding a list of numbers, try to find pairs that add up to 10 nicely. In this example, we have 8 plus 5. That's only two numbers. But if I look at 8 as 5 plus 3, then I can easily make 5 plus 5 plus 3. The two 5s would make a 10. Or I can split my 5 up, and I can say I know 8 plus 2 is 10, so I can split 5 into 2 plus 3. 8 plus 2 plus 3 looks like 10 plus 3. So we can break numbers down to make them easier to add in our head. If we're looking at subtraction, there's a few models that we can use. The takeaway model is probably the most common one, and that's where you start with a certain number of manipulatives, like blocks, maybe just on the table. Start with 8 blocks on the table, and we want to model 8 take away 3. So we take 3 of the blocks off of the table and then count what's left. We can also use something called a missing addend model. Subtraction and addition are closely related. They are inverse of each other. So if I am subtracting two numbers, I could reverse that problem and make it an addition problem. For example, 8 subtract 3, I can rewrite that by adding 3 to say 8 is equal to some unknown number plus 3. For some reason, our brains work better when we count up than when we count down. And maybe not everybody is like that, but I know it's true for me. If I had to think about 8 take away 3 versus something plus 3 to get 8, my brain quickly jumps to 5. So we can rewrite any subtraction problem as a missing addend problem, where we just have an empty box that represents the same value as the answer to the subtraction problem. We can use the diagram of the blocks on the table, the same takeaway model. We can kind of use that to represent the missing addend model. We can start with the 3 blocks that we have on the table and ask how many more would you need to get to 8. And this is a great transition to using counting up for subtraction. If we're doing something like 8 minus 3, maybe you've heard somebody tell you before, start at 3 and count up. Well, that's exactly what this model is helping illustrate. If you tell somebody start at 3 and count up, but you don't explain why, they might not do it right. They might start at 8 and count up 3. Or they might just not use the trick altogether because it doesn't make sense to them, and math is supposed to make sense. I have a number line here to help illustrate the counting up idea. Now, On this number line, we have 8 and 3 that are both starting at the origin at 0. And this is doing a missing addend right here. It's saying how much more do we need to get up to 8? If we started at 3, we could count up 1, 2, 3, 4, 5 to see we would need something that's 5 units long to get up to 8. We can also use a comparison model, which is a lot like what we just saw on the number line. If we're looking at a subtraction problem like 8 minus 3, we can say, well, maybe Juan has 8 blocks, Susan only has 3 blocks. How many more blocks does Juan have than Susan? This is just another way to model difference. How different are the numbers of blocks that Juan and Susan have? A lot of times students will have a hard time noticing that this is a subtraction word problem. But if you start to model it, then you can see the physical representation of the problem, and you can understand that it is subtraction because we're trying to figure out how different the number of blocks are. We can use a number line for subtraction. Any number that we are subtracting, we would flip the arrow around to be backwards. So the way that this number line starts, you start with your first number, which is 5. Represent that on the number line. And then if we're subtracting 3, we're going to start right in line with where our first arrow stopped, but we're going to draw our arrow backwards to count backwards 3. And then wherever that stops, that would be our answer. So stopping at 2. Now, algebra sounds like a scary word, and that's mostly taught. Adults telling you algebra is hard, that math is hard, that if you put letters in with your numbers, then it's hard. But the truth is, it's just like the missing addend. So we can create number sentences that basically introduce students into the idea of algebra early on without overwhelming them too much. So we can make sentences like 9 plus 5 equals sunshine, or 12 minus diamond equals 4. And we can show them that these statements are true or false depending on what sunshine is equivalent to and what diamond is equivalent to. So we're going to get away from using the letters because for kids, letters already have meanings, numbers have meanings, but these shapes, sunshine and diamond, are completely meaningless in this context. So we can show them it's just a placeholder. And then we can step it up by letting each of these values take on some numerical value. So if we let sunshine be equal to 10, then we can see that number sentence 9 plus 5 equals sunshine is false. And if we let diamond equal 8, then we could see that the number sentence 12 minus diamond is equal to 4, which is true. So we can evaluate each of these sentences and determine if they're true or false.